Hey everyone, welcome back to our discussion of section 4.4. Last time we learned about the second derivative of a function and how it can be used to study the concavity of the graph of the function. In this section, we will finalize our discussion of concavity by seeing the second derivative test, which allows us to classify local extrema using the second derivative. After that, our primary goal will be to see how we can use everything we've learned about functions to sketch graphs of those functions. The point of this exercise isn't to simply graph the functions, but also to realize how local information can be used to get a sense of the bigger picture. In the last video, we were introduced to the idea of concavity of a graph, and we saw how the second derivative is related to it. Now let's see how we can apply this notion to classifying critical points. In front of you, you'll see the full statement of what is known as the second derivative test. Notice that there are three possibilities. Let's start by focusing on the first two. To understand these two statements, I think it's best to look at the two graphs drawn below. In the first graph, you'll see a local maximum. Notice that in this case, the tangent line at the local maximum is horizontal. Because it's a local maximum, you can see that the function appears to be concave down. That's all the first bullet says. It says if the derivative is 0 at a point, or in other words, the tangent line is horizontal at that point. And in addition, the second derivative is negative, or in other words, the graph of the function is concave down, then that point must be a local maximum. The second bullet is the equivalent for local minimums. If you have a critical point with a horizontal tangent line and positive second derivative, then the function is concave up and the critical point is a local minimum. So before we study the third point, let's compare the second derivative test to the first derivative test. The second derivative test allows us to test if something is a local maximum or minimum by plugging in the critical point into the second derivative. The first derivative test, on the other hand, requires you to know where the first derivative is increasing and where it's decreasing. This takes a lot more work than simply plugging in one value into a function. So hopefully you're all wondering why even bother learning the first derivative test. The answer to that question can be seen in the third point of the second derivative test. The third point says that the second derivative test fails anytime the second derivative is also 0. To see why, let's look at these three graphs shown below. All three of these functions have a horizontal tangent line at x equals 0. But unfortunately, all three of these functions have the second derivative equal to 0 when x equals 0. Notice that the first function has a local maximum at 0, the second function has a local minimum at 0, while the third function does not have a local extrema at 0. If you continue on, you will eventually study multivariable calc, where you study functions that depend on more than one variable. As a result, their graphs will be higher dimensional. In these higher dimensional settings, it turns out there is no equivalent to the first derivative test. In that setting, there is still a second derivative test that also has a failure condition similar to this one. Critical points at which the second derivative test fails are often called degenerate critical points. Since the behavior of functions near these degenerate critical points can be so horrible that the theory often assumes that there are only non-degenerate critical points so that the second derivative test will apply. So let's compile everything we've learned, both in this class and the ones that came before it, about the various properties of the graph of a function and the different techniques we can use to determine what they are. We will use all these different ideas to get an idea of the shape of the graph of a function. Notice that the vast majority of things on this list are based on the calculus we've learned this semester. So before you start panicking and memorize everything on this list, let's look at some of the major features. First of all, notice that this list is organized into information you can get from f, its derivative, and its second derivative. Second, realize that I've colored parts of each list the same color. I've done this because in order to find these properties, you go through the same procedures effectively. For example, in red I have highlighted finding the zeros of f, finding the critical points of f, and finding the inflection points of f. In order to do all three of these, you set f to 0, f prime to 0, and f double prime to 0, respectively, and solve for the corresponding x values. There is the added step of having to find out where f prime and f double prime don't exist to find critical points and inflection points. It is also important to check that your solutions to f double prime of x equals 0 are actually inflection points by checking that the concavity actually changes at that point. One last thing, notice that I listed both the first and second derivative test on this list. In reality, you only have to do one or the other to determine what kind of critical points you have. It's up to you which one you choose to use. There is no right choice, and either can work, but often one is a better choice than the other, but which one usually depends on the function you're working with. In the rest of this video, we will put what we just said into practice by working through two examples. It might be helpful to have the list that we just created in front of you as we work through these examples. In our first example, we are going to sketch the graph of this cubic polynomial, x cubed plus 3x squared. So we will start by finding the zeros of f. To do this, we set f of x equal to 0 and solve by factoring. Next, we figure out what f is doing at infinity. We do this by taking the limit as x goes to positive and negative infinity. We see that f is going to positive infinity and negative infinity at negative infinity. This tells us that f does not have any horizontal asymptotes. This isn't surprising because polynomials that aren't constant have no horizontal asymptote. Also, since f is a polynomial, we know it's always continuous and doesn't have any vertical asymptotes. For that reason, we will skip that step here. We will now make a chart like you've seen in previous videos to determine where f is positive and negative. Great. So on to f prime. We will now find the critical points of f. We do it by first looking at when f prime is equal to 0, and second, when f prime doesn't exist. Since f is a polynomial, we know that f prime will always exist, so we really only have to do the first step, but we show both for the sake of completion. Next, we will find where f is increasing and decreasing by finding where f prime is positive and negative. I will save everyone time here by skipping the chart and just writing down the result. At this point, we will use the first derivative test to classify the critical points of f. At the critical point at -2, we see that f goes from increasing to decreasing, so -2 must be a local max. While at the critical point at 0, we see that f goes from decreasing to increasing, so x equals 0 must be a local min. We will now work with f double prime. We find the inflection points just like before by setting f double prime equal to 0 and solving by factoring. Remember, just because f double prime of -1 equals 0 does not make it an inflection point. We still need to make sure it's an inflection point by checking where f double prime is positive and negative. The good news is this will also tell us where the graph of f is concave up and concave down. So, two birds with one stone. We will now use the second derivative test to classify the critical points we found before. Since we've already done the first derivative test, this step is not strictly necessary, but we're going to do it anyway, since we haven't actually seen the second derivative test used in an example. Notice that f double prime of -2 is negative. That makes it a local maximum. F double prime of 0 is positive, which makes it a local minimum. Since we've done so much work, I would suggest collecting everything we've done into one page so that we can have it in front of us when we finally draw the graph. You don't always have to do this, but I recommend it, especially while you're getting used to this process, because it's useful to see all the important information in one place. Since this is basically copying down everything we've already done, I'm going to speed through this part of the video. You should feel free to pause the video as much as you need throughout this to make sure you see all the information we've computed thus far. Okay, so we can finally start sketching the graph of this function. First, we'll draw in our zeros and the behavior of our function at infinity. We will next plot our critical points. I think it's useful to make some sort of mark that help you remember later which critical point is a local max and local min, or neither. I use these kind of valleys and peaks. Next, we're going to draw in the inflection point. We know that at this inflection point, our function goes from concave down to concave up. So once again, I'm going to make a mark at that inflection point to remind myself of that for the last step. So with only this much information drawn in, we can already see the general shape of this graph coming into view. So I will now connect all these different features together into one graph. I think it's important to remember that these problems are usually worded as sketch the graph. I hope you can now see why. So now for good form, let's compare what we've sketched to the graph of this function made by a computer. Isn't it a great feeling when a computer confirms what you did? Okay, let's try one more example. This time we'll do a rational function. Since much of the work is similar to what we just did, I will move quickly through it, slowing down only to point out the major differences. As always, I encourage you to pause the video as much as you need. Okay, like before, we're going to start by computing the zeros of f. Since this is a rational function, those zeros only occur when the numerator is equal to 0. Since g of x is a rational function, we know it'll be undefined anytime the denominator equals 0. So we can find them to know what points are not in the domain. So now let's figure out what g of x is doing at positive and negative infinity. We do this by taking limits as x goes to positive and negative infinity. We see that in both directions the limit is 2, which means y equals 2 is a horizontal asymptote for g. So now we'll figure out where g is positive and negative. I will point out we didn't explicitly use this in the previous example, but this kind of information is useful to check that the rest of your work is correct. So unlike the previous example, this rational function has points at which it is not defined. We know that the line x equals 1 and x equals negative 1 are both vertical asymptotes for g. So let's figure out what the behavior of g is near these asymptotes. So we take the limit of g of x as x approaches negative 1 and 1 from the left and from the right. This tells us that g is going to infinity as it approaches negative 1 from the left and 1 from the right. And it's going to negative infinity as it approaches negative 1 from the right and 1 from the left. Okay, great. Now we'll find the critical points of g. We take its derivative as always. First we check when g prime of x is equal to 0, and we find that x equals 0 is a solution. Now we find when g prime of x does not exist. In this case, it doesn't exist at x equals plus or minus 1. But I'll remind you that at x equals 1 and x equals negative 1 are not in the domain of g. So even though g prime of 1 and g prime of negative 1 don't exist, they are not critical points of g. Now we will find the intervals on which g is increasing and decreasing. So notice that for all negative values of x other than x equals negative 1, g prime is positive. So g is increasing on those intervals. When x is positive and not equal to 1, g prime is negative, so g must be decreasing on 0, 1, and 1 to infinity. So now we move on to g double prime. First, we find any candidates to be inflection points. The numerator is never equal to 0, and g double prime exists everywhere but at x equals plus or minus 1. Like before, x equals 1 and x equals negative 1 are not in the domain of g, so neither of these are actually inflection points. In fact, g has no inflection points. So this time through, we skip the first derivative test. Let's use the second derivative test to classify the critical point at x equals 0. We see that g double prime at 0 is negative. Thus, g has a local maximum at 0, 0. Alright, it's been a long haul, but we're almost done. We'll start by drawing the vertical and horizontal asymptotes. We know that as x goes to positive or negative infinity, g goes to 2. We also know that as x approaches 1 from the right, g must go to positive infinity. So we'll draw that in on the interval 1 to infinity. For similar reasons, we know what g must do from negative infinity to negative 1. So let's go ahead and sketch the graph of g on these two intervals. So to complete the graph, we know that g goes to negative infinity when you approach negative 1 from the right or 1 from the left. And we also know g has a local maximum at 0, 0. So when we draw that in, the rest of the graph sketches itself. So just like before, we are happy that the graph matches what a computer says the graph should look like, or at least roughly matches what the graph should look like. So thanks again everyone for sticking with me through this video. I know it was rather long, but that's just what happens when you're trying to graph things by hand. I hope you all got a feel for what it's like to use a bunch of local ideas, like inflection points, local mins and maxes, and zeros to help us get a sketch of what the graph of a function should look like. Again, where a function is 0, where a function's concavity changes, where a function's derivative is 0, is all local behavior, but at the end of the day, we ended up with a fairly accurate global picture. So I'd like to thank Ashley Kang again for all the help she gave me making this video, and I hope you all have a great day. See you in the next video.